Okay, so under the oxides, you have hematite group, rutile group, and spinel group, right? So because of their rare occurrence, we can consider them also as economic minerals or industrial minerals, which have some industrial applications, right? What is next? So iron titanium oxides. So we considered iron titanium oxides here. For example, ilmenite, right? So you have iron titanium oxide there. There are some N members actually, right? Under this group, you have N members. So what are the N members? You can see this triangle. You can see this triangle where one corner is titanium dioxide, okay? TiO2. So TiO2 in mineralogy we call rutile, okay? Right. The other corner you have iron oxide, FeO. And here you have Fe2O3, and in the middle you have Fe3O4. Right. So these are solid solution minerals. So what do you mean by solid solution minerals? Have you learned it? Solid solution. How do you understand solid solution minerals? Any idea?
Minerals are mixed in solid states.
Yes, they have mixed in solid state. For example, when we have iron and magnesium, for example, in a mineral, with temperature, their composition can be exchanged, can be changed, right? Sometimes this proportion can be 50-50, and sometimes it might be 30-70 or 80-20 or something like that, right? So but these minerals never go into solution to make their adjustments, right? So they change their compositions under solid state conditions. So therefore, we take them as solid solutions because solution mean it's a mixture, right? But usually solution is a liquid matter. But here, although the composition are mixing together, the species are mixing together, but that is happening under solid state conditions because of diffusion, right? Because of diffusion, this diffusion is controlled by the temperature mainly. Pressure also matters, but much is controlled by the temperature. So therefore, we consider them as solid solutions. So you have solid solutions in between these groups of minerals. Okay, so basically you can see this ulvospinel, ilmenite, rutile, and like that. There can be some compositional variations, and these variations also have some group names also, right? Series, different series, because they are the mostly common occurring minerals under this iron titanium oxide groups. For example, if you are looking for a composition somewhere here, right? Somewhere here you will basically see rutile only, right? The very less amount of intermediate compositions falling at this region where you can see this arrow, right? But at the corner you have a lot of rutile occurring, but there are some other minerals which are occurring along this line, okay, along this line. Like that, you have more compositions along this line also, and also along this line, right? So that means it's not really a straight line, some region like this, okay? If you plot the compositions after analyzing by an electron microprobe, you can see if you plot various samples, right? You will see they are plotting here and there, but basically along a series like this, okay? So also this type of occurrences are available regarding these iron titanium oxides. And next what you have is spinel group. So we considered spinel group before. The basic formula is this one, right? Two metal ions are there, and it's sort of very complicated, right? It's three-dimensional because you have such a variable composition there, right? So iron titanium is variable along this line, okay, and magnesium is also variable. For example, you can see magnesium titanium composition here, right? It's although we just consider for simplicity as x and y, this x and y again can be replaced by various minerals, various elements, right? So although we consider x at the beginning, right, spinel group here, x can be magnesium, y can be aluminium, right? So we have some other species also, chromium, beryllium, likewise, right? So this composition can be variable. So therefore, this is a little bit complicated because this is the group which has a complex chemistry, right? Solid solution chemistry. And you can see here magnesium and titanium is there, okay? Magnesium is titanium is mixed, and here magnesium and chromium is mixed. And here you have magnesium and aluminium is mixed. And this is so-called normal spinel, right? Magnesium and aluminium, right? So this is again you have this magnetite site, right? Magnetite site. You have composition towards this way, right? Without having here, right? And here again iron titanium, ilmenite site. So likewise, this composition is very variable. A lot of complex chemistry is there because chromium, titanium, aluminium, ferrous, ferric, everything is coming onto this composition, right? So you can see here chromite is there. This is what we call chromite, right? This chromite, and this is normal magnesium spinel, right? This is normal magnesium spinel. When it mixes with iron, they are getting a little bit the chemistry little bit variable, and also at the same time color variations and many other changes are happening. So for example, when the chromium is dominant, this spinel becomes more yellowish or brownish, not brown actually, honey brown, like yellowish color. It is considered as a gem also, semi-precious, and normal spinel, you know, it's considered as semi-precious gemstone, and greenish spinel, and also pink spinel. All those are there, right? So this variation, the chemistry variation matters for this spinel. So you can see here even bluish ones, pinkish ones, and like reddish colors. And this blackish appearance, right? This blackish appearance is very common in ultramafic rocks. This spinel is common in ultramafic rocks. Ultramafic rocks means heavily magnesium rich rocks, right? Peridotite, you may have heard the gem called peridot. It's coming from peridotites. It's olivine. It's totally olivine. So olivine rich rocks, you have spinels also, right? Most probably this light greenish one is olivine, right? Peridot. So that is available in such rocks also. So therefore, the chemistry is very complicated in spinel group, right? But anyway, it is a very nice oxide group because we can have variation in colors, which is considered as a lot of beautified stone, like naturally beautified stones. And you have other common oxides in addition to the previous ones that I mentioned. Rutile, titanium oxide, corundum, aluminium oxide, right? You see this beautiful hexagonal shape, corundum. And pyrolusite, manganese oxide, right? Pyrrolysite. It occurs as dendrites. You know dendrites? Have you heard of dendrites? Anybody? Usually on rocks on fracture surfaces, right? So if you have a fracture surface of a rock, right? This is a face, one face of which has been developed a fracture. Okay, so here on this fracture surface, you might see some tree-like structures, like some branching, right? It looks like a fungus or something like that, right? Very beautiful, very nice structure, like some network of trees, like branched trees, like, right? So you have branches like this, right? So these are dendrites. We call dendrites. You can see dendrites here. On the surface, you see dendrites here, the tree-like features in this region, right? See, branching is available. So that is pyrrolysite, mostly pyrrolysite. It's manganese oxide. And sometimes this pyrrolysite grows in 3 dimension. We call botryoidal pyrrolysite, right? It's like nodules, like manganese nodules, like thing, right? Manganese nodules, you know, that is again something like this, right? In the sea floor, you have this type of manganese nodules. So this is pyrrolysite anyway. And what else? Chrysoberyl. Chrysoberyl is there. And this is a twin crystal. Chrysoberyl twin crystal. And sapphire, that is corundum, right? And ruby is there. Corundum family. All these are oxides. So oxides are, I think, very popular because of their occurrence as gems, right? And some quartz contain some of these rutiles as needles, right? So you see some needles are there, and inside quartz, it's giving a very beautiful appearance to the quartz crystal, right? As inclusions. Sometimes you might see tourmaline also like this, but it is a different mineral. It's a silicate, borosilicate, but you can see similar textures. Right, hydroxides. The other group is hydroxides. So hydroxides, you know, they contain OH group, right? Hydroxyl group. Hydroxyl group is there, right? So that is the main anionic group. Main anionic group in this type of minerals. Okay, they form octahedrally coordinated sheets, right? Octahedrally coordinated sheets. So what is octahedrally coordinated sheets? Octahedron, you know, I think, right? This one unit is a octahedron, right? So you have sheets of these octahedrons. So this is one sheet, okay? And this is another sheet, octahedral sheet. So they are interconnected. They are connected together as coordinated sheets. In between, you have van der Waals forces. Van der Waals forces, that those are not very, very strong. So here you have two types. One is called brucite type, where trioctahedral sheets are there. That means there are 3 octahedral sheets, 3 sheets, right? So in this octahedron, you have oxygen here, oxygen atom here, which act as a bonding agent in between, right? So therefore, we call this as a bridging oxygen, in all tetrahedral sites. So you can see they are all filled. And the other type is gibbsite type. So the other type is gibbsite type, where you have the dioctahedral sheets. dioctahedral sheets. Dioctahedral sheets, where you can see some kind of like this. So you see these two is a single layer. It's a dioctahedral sheet because you have two sets, right? You have two sets, and these two sets are bonded with another two sets, similar two set. So therefore, they are called dioctahedral sheets. Dioctahedral sheets. So one sheet is composed of two octahedral layers. Dioctahedral sheets. But you can see some blanks in between. For example, here, right? Here, some blanks are there. That means there is no total filling, right? They are not fully filled. The sites are not fully filled. But here, brucite type, you don't see such vacant areas. Everywhere it's filled, totally filled. So therefore, all octahedral sites are filled, we call, right? So these are the types of hydroxides which form as octahedral types, brucite type and gibbsite type. So as some common types, there are many hydroxides, but some common types of hydroxides are brucite. So you have brucite here, so that's why we call it brucite type also, the main mineral. So under that group, brucite type, so under that group we have this set as the common types of hydroxides. Manganite, manganese hydroxide. So it is coming as oxide hydroxide. Okay. Then goethite. You have goethite, right? It's iron oxide hydroxide, right? Because they are not much. I mean, this iron, manganese, like ions, cations, do not prefer much hydroxyl ions, but the oxide can make some complexes with that, right? But unlike those, magnesium is very reactive, and they can straight away bond with hydroxyl group, right? So that's why you have this one. The other group, which is a gibbsite group, that means this group, you have gibbsite, the mineral gibbsite, aluminum hydroxide, and diaspore. Diaspore is aluminum oxide hydroxide, right? This is aluminum hydroxide, right? This is different because there are some number of alpha. That means a few numbers of aluminum hydroxide is connected with hydroxyl. Right. Okay. Then comes bauxite. So you know bauxite already. It's aluminum hydroxide. It's aluminum hydroxide, but it's a kind of mixture. It's a kind of a mixture. Diaspore, gibbsite, and boehmite. Boehmite is aluminum oxide hydroxide, right? So everything together. It's not a single component. It's a mixture, right? But since all are hydroxides, associated with hydroxide, mixed with hydroxides, it is considered as a the compound of, complex compound of made of hydroxides. So bauxite, aluminum hydroxide. So it's basically these are aluminum ores, right? They are considered as aluminum ores. Aluminum ore means it's an ore deposit which you use to extract aluminum. Right. So next group is halite. Okay. Next group is halides. So you know halides also. Halides are formed as a result of reactions with halogens, right? Halogen anions. So they are anions, you know, -1, chlorine, bromine, fluorine, iodine, right? They form typically isometric ones. So that's why you had this fluoride, calcium fluoride, CF2 as isometric cubic tape, right? So they form ionic bonding also, right? They form ionic bonding. And the properties are usually they are low hardness. Unlike other minerals that we considered, they are having low hardness, right? Easy to break and easy to, not break, easy to wear and tear. So therefore it's low hardness and high melting points, but high melting points, right? To melt, you need to heat to a higher temperature. And also poor conductors, as you know, halogen do not conduct, right? They do not prefer conducting electricity, but at very high temperatures, they might conduct electricity. Under normal conditions, or under room temperature, or little above that, they are insulators, right? Right, so as common halides, what we have, halite, right? You know halite, sodium chloride. Sometimes another name, can you tell me, anybody? Another name for halite? Think.
Salt.
Yes. Halite. We call, yeah, somebody.
Rock salt.
Yes, that's right. Yeah, rock salt. So it's rock salt. Rock salt means huge rocky salt deposits you can find in the oceans, right? It's rock salt. It's you know, it's very crystalline shape, right? And then potassium chloride, that is sylvite, right? Sylvite is potassium chloride. And the other one is fluoride, right? Calcium fluoride. Those are common halides we have. Right. So next we can consider carbonates. What are the carbonates? So you know already carbonates, right? For example, calcite, aragonite, right? So what is aragonite and calcite relationship? There's a relationship in between these two. It's the same compound. That is what is calcium carbonate. Okay, calcite is calcium carbonate. Aragonite is also calcium carbonate. But the only difference is calcite is low pressure variety, and aragonite is high pressure variety. So in the ocean you can find these two. If you go down to the bottom of the sea, you will more likely to find aragonite, not the calcite. Right? Calcite is low pressure, aragonite is high pressure. So when you go deeper, the pressure is increased. So deposited or precipitated calcium carbonate change into aragonite form, right? So that's the it's the same compound, but two polymorphs. Okay, right. So you can see these calcites are associated with other materials like dolomites, right? So what is dolomite? It's magnesium carbonate. Okay, it's magnesium carbonate. So pure calcium carbonate you can consider as calcite, but when it mixed with magnesium ions, so that means it's also like solid solution behavior, right? Calcium, instead of calcium, there is possibility for magnesium to replace, so then it becomes dolomite, right? If the majority is magnesium carbonate, calcium magnesium carbonate, and that means magnesium is dominant there, you can call it dolomite, not calcite, right? And you have anchorite. You have anchorite. There you have iron. Iron replacement is there. Anchorite. So you may see siderite. The other one siderite. That's iron carbonate, right? This is calcium iron carbonate. This is pure iron carbonate, right? It's siderite. And magnesite. That's a white color material. See here. It's magnesite. Magnesite is magnesium carbonate. So all these things are industrial minerals because they have various industrial applications. Therefore, they are popular industrial minerals, and also they are not toxic also, right? Unlike the halides, right? These are a little bit toxic. Silvite, halite is not toxic much, but it contains a lot of trace elements. Therefore, it's not suitable for consumption as stable salt, right? So anyway, mostly these carbonates are hexagonal type, hexagonal. Okay, so you have magnesite, dolomite, and calcite, pure calcite. Dolomite is always calcium and magnesium, right? Remember, calcium and magnesium carbonate. Then you have the anchorite, iron bearing. And finally, you have siderite, iron carbonate, as iron carbonate. So this is the compositional variation or trend with respect to these carbonates.
Excuse me, sir.
Oh yeah.
Would these all chemical have the same crystal structure?
No, they all are not the same. They are different. So you can, they're not necessarily to be in the same structure. Some are orthorhombic, some are hexagonal. Likewise. So you can check their crystal structures as well and compare them. Right? They are not all of the same structure. And in this triangle, you have the most frequently found compositions. For example, in this region, right, this marked region, you have this carbonate composition where dolomite towards anchorite composition, right? But it does not continue like this, right? It does not continue like this. So that anyway, there are some immiscible region. We call these type of regions as immiscible. For example, here no composition is there, right? So here also no composition. So these are called immiscible regions. That means, for example, dolomite and magnesite cannot mix together to form an intermediate composition, right? Instead, what you have mixing agent here is magnesite and siderite, right? Like this. You can have some composition, but not in the opposite direction, right? So you have calcite also. Calcite, but calcite, it does not react with iron or anything. It only reacts with quartz to form some other minerals like olivine, like minerals. Okay, right. Some other carbonates, in addition to these carbonates, you can consider azurite. Right, it's a very important mineral in industry. Azurite. You see here, very beautiful purple color, right? Like here, it's very beautiful color. So this is the typical feature of azurite to identify, right? So if as soon as you see this typical peacock blue color, so it's a peacock blue color, okay, you can really recognize it as azurite. And mostly this azurite mineral is associated with this greenish varieties also. So what are these greenish varieties? Why they become green? What do you think? Guess.
Copper?
Yeah, copper. They contain copper, therefore they can become greenish in appearance because it is again hydroxyl ion is also there, right? Although it's a carbonate, some adsorbed hydroxyl ion is also there, right? Adsorbs. It is like sticky into the structure, right? Aluminum copper carbonate structure. You have this hydroxyl group adsorbed. And malachite, this green one is malachite because it's purely containing copper, right? Purely copper. It's the proportion is very different there, right? So cupric and cuprous varieties are there for these two, right? And this one, manganese carbonate, that is rhodochrosite. So this is also a common, not common, not very common, but it's a popular mineral, rhodochrosite, because of this color. It's popular because of this color, this very beautiful pinkish appearance. So this is rhodochrosite. It's purely manganese carbonate. It's purely manganese carbonate. So then after carbonates, we can consider borates. As the term itself explains, borates are the ones which have boron in their structure, right? Boron is there in the structure, which you call borates. Okay. So you have this kernite, that is sodium borate, but still you can see it's a hydrous. It's hydrous, that means it contains water, OH as well as H2O. So this H2O and OH, both groups are there in the structure, right? So this OH we call structurally bonded water, and this H2O we call adsorbed water, right? It's just adsorbed to the structure only. It's like sticky behavior. It's not really inside the structure. What is really inside the structure is OH group, hydroxyl group. And then you have borax. You have borax here. That is sodium borate. Again, the chemistry is a little bit different. And also the adsorbed water amount is high in that structure, borax. And ulexite, the other one is very rare one, ulexite. That is calcium also contained in the structure, right? Calcium is also there. It's a sodium calcium bearing borate. Okay. Right. Then we have another group, that is sulfate. that is sulfate group. This sulfate group can be two sub categories: hydrosulfates and anhydrosulfates. So hydrosulfates, like gypsum, hydrosulfates, they belong to gypsum group, and the other one is alunite, right? Alunite means aluminium bearing, and potassium also there, sulfate, right? It contains OH also in this structure. It's not like the previous form. They are like well adsorbed amounts of water molecules are there, either in the form of OH hydroxyl group or the H2O molecule, like, right? Adsorbed or structurally bonded water. And the other group is the anhydrous group. This is what you have here, anhydrous group, and the name of this mineral is anhydrite. It's anhydrite. It's calcium sulfate. Calcium sulfate. Okay. It's anhydrite. Sorry, in anhydrous form, right? No water there. Like in gypsum, you have water, but here you don't have any water. Then barite, barium sulfate. You have barium sulfate, barite, as another sulfate mineral. So these are some types of industrial minerals that we consider under rare occurrences, right? So oxides and hydroxides, sulfates, all these belong to that group which we are considering now, right? And because of their rareness, although they are not much used in industry, they have good demand for various applications. It might not be very heavy industrial work, but just for separation of some, for example, production of sulfuric acid, like, they might use these sulfates also, right? So such kind of applications are there apart from the other types of industries. Tungstates and molybdates, the other two types of groups, tungstates and molybdates. And wolframite, maybe wolframite you may have heard before. That's iron manganese tungstate. Tungsten is W, right? Tungsten is W, tungstate is this one, right? Wolframite, then scheelite, right? So these are very illuminating, right? If you especially scheelite, right? This scheelite, if you have a torch with sort of what you call UV lamp, right? If you have a UV light, they will be very how do you call fluorescent, right? They have the fluorescent feature. They are very shiny, okay, under UV light. Then there's another one, very rare one. It's a wulfenite, which contains lead also, which contain lead as well, right? Lead and molybdenum in the form of an molybdate. So here you have tungsten, here you have molybdenum, right? Molybdenum and tungsten are there. Okay, so the another group is called phosphates, right? Phosphate, you know already. In Sri Lanka also we have phosphate. Where do we have phosphate? In Sri Lanka.
Honeycomb beds?
Yes, in Vandi complex we have. Where about the location?
Eppavala.
Yes, that's right. Eppavala, you have phosphates. Eppavala apatite contain phosphates. So you have this, they are a little bit complicated. The chemistry is complicated because some halogen and water is also attached to these apatite grains. So beautiful crystals you can see here. In Eppavala, you may have seen very large crystals like the size of a person, human size apatite crystals with very nicely shown faces also, right? So these are sometimes they are common in hydrothermal deposits as well. Even previous ones are also very much available in hydrothermal deposits, okay? Except for these carbonates. Right? Carbonates are mainly precipitates from sea creatures, sea animals. And these phosphates may also have some variable colors, right? Based on some trace element inclusions, some colors can be changed. So bluish, greenish, yellowish, and colorless even phosphates can be found. Right. So another common phosphate is monazite, right? You know monazite already. Do you know monazite deposits we have? Where about monazite deposits we have in Sri Lanka? Okay. So monazite deposit is available in Pulmude, you can get some monazite, but mainly in Pulmude, what you have is ilmenite and rutile, and also some zircon. Monazite is very limited. In the western coast, we have monazite deposits. Offshore monazite deposit is there. Actually, it's not far from, I mean, it's not in very deep sea. In the coastal region of Beruvala. Okay. In Beruvala, you have monazite deposit region. And also southern Sri Lanka also you may get some monazite deposits, but not that much. Right. Then wavellite deposits you can find as and sorry, I forgot to mention that this monazite is very characteristic because it contains rare earth elements, REEs. Okay, so these are called RE, rare earth elements. So these are RE deposit. Sometimes we call RE deposits because they contain a lot of amount of rare earth elements. So you can see there are no major element here, right? Iron, magnesium, chromium, or anything is not there, right? Instead of those, what you have is rare earth elements: cerium, lanthanum, yttrium, thorium, like that, right? So if you have a monazite deposit, then it can be considered as a rare earth element deposit, right? Because of the dominance of rare earth elements in the monazite structure. And people use monazite also for age dating in rocks, right? Normally we used zircon, but monazite can also be used to determine the age using isotopes. Then wavellite is a aluminium bearing phosphate. It's like some globular characteristics are there in the mineral, globular. You see here, globular characteristic is also there, right? Then turquoise is there. That is copper aluminium phosphate. copper aluminium phosphate. So you can see it's a bluish color is there. Bluish color is there. Right, turquoise. Right? These are actually a little bit rare minerals. Okay, so far we considered about some groups of minerals which are found rarely as industrial minerals. So, but oxides are there anyway. It's not rare. Like silicates, even these oxides might be found. So you have hydroxides, halides, carbonates, borates, sulfates, tungstates, molybdates, and phosphates. So these are the ones that we just consider as some rare types of industrial minerals. In addition to the ones that you already know as very common type of industrial minerals, for example, feldspar, quartz, calcite, dolomite, rutile, ilmenite, and monazite. Ilmenite and zircon. Right. In addition to those, the other groups are also there. Other mineral groups are also there as industrial minerals which we can consider. Right. So, any question out of this section? I did not go through very detailed because this is a totally mineralogy lesson actually. I mean, it's a different lesson, but since it has a relevance to your field and applications, I think it's worthwhile discussing on that. Right, so you can go through the websites of some mineral related pages and find more details if you need. Specifically related with their occurrences, right? Because most of these minerals occur in relation with some igneous processes, right? Igneous crystallizations. So therefore, maybe you can just go through some sources where you have various details regarding these ones. Okay. Right, no question? Okay, so if no questions, I want to move to the other section. Another category is there, right? Which is remaining for us to consider. That is also important and interesting. So, sorry, not this one. Yeah. Okay. Native elements. So what are the native elements? So, you know, native elements means the freely occurring elements as metals, right? Mainly metals, types of metals, right? So, of course, metals are further subdivided recently. Based on their chemical properties, based on their chemical characteristics, right? The most reactive ones are taken as metals, and then semi-metals, and finally non-metals also, right? So native elements means the elements or the minerals which occur as elements and the pure form of elements, as the pure form of elements. So examples are gold, right? You know, gold and gold and silver, gold, silver, gold, silver, copper, platinum, palladium, osmium, iridium, iron, and iron nickel, right? Because nickel, most of the cases occur in association with iron, right? So sometimes people call iron nickel deposits, like, right? Those are metals. native elements, the elements which the resources which occur as pure elemental form, right? Then you have semi-metals, as I mentioned, arsenic, bismuth, antimony, likewise, trace, but D block elements also comes under this, right? And then non-metals. What are the non-metals? Non-metals are sulfur, diamond, graphite. They all are in elemental form. This is S, sulfur, diamond is carbon, graphite is also carbon, right? Those are elemental forms. So we consider them as native elements, So out of that, we can consider native metals, which is considered as the native type of an element. So they are characterized with the metallic bonding. So being metals, they prefer metallic bonding, right, in between. And their properties are dense, cubic, close packing, right? Then we have dense, cubic, and close packing of atoms in the mineral lattice. Therefore, they are pretty heavy and robust. Properties, they can, I mean, the structure wise, they can be deformed, that means malleable, but they last long because of this close packing. They don't get easily destroyed, right? The pure form, 100% pure form, is very soft, these native metals, but ductile. The reason is ductile. They can be changed into different shapes of shaped forms, and sectile, easily sectioned. You can easily split them, section them, and good conductors, both electric and heat conductors, good conductors. And also they have variable melting points, as you can imagine. Variable melting points, relatively, if you line them up, the lowest will be gold, and then silver, then copper, and the highest will be PGEs, platinum group elements. Okay, melting points, they have very high melting points in PGEs. So platinum group elements here: platinum, palladium, osmium, iridium, yeah, those are the main metals under the platinum group elements. Rhenon is also there, but it's not widely considered as a metal, right? So they have melting points, variable melting points, right? And they are used much for the ornamental things and the jewelry market. So they are also being extracted in large scales. Unlike some of other categories, these are very expensive. Therefore, they haven't given up these mining tasks. So the melting point is very much high in this order, right? If you consider this order, the melting point is getting increased. PGs have the highest melting point, and the platinum is very expensive, even more expensive than gold, right? Platinum is very expensive, and also they are being rare. That also adds huge amount of value for them. Okay, so then what you have is native non-metals, right? So far we consider native metals, right? So we have non-metals. We have non-metals also, and native non-metals. As non-metals, you can consider sulfur, because they occur as it is, sulfur, right? As the element itself, you can find sulfur associated with volcanoes. Okay, so it's a kind of weak van der Waal forces bonded structure is available for sulfur, right? It's a ring type of molecules, circular type of molecules. Like I think if you have done silicates, you may remember the cyclosilicates, right? Okay, so you have diamond then. They have also very, very strong bonding, and graphite that is weak. Their forces are weak, unlike diamond. So that's why they are behaving like slippery feature. That means lubrications, it's ideal because of this sliding feature, right? So weak van der Waal forces are acting in between their layers. And sometimes you can consider diamonds also, industrial grade diamonds, but those are synthetic diamonds. Okay, those are synthetic diamonds, not the natural diamonds, right? Natural diamond, of course, you can consider because that is also a non-metal, right? It does not conduct electricity or not good heat conductors, right? So where these native element occurs, as we considered before, normal compounds like that hydroxides, oxides, and other ones, they are associated with magmas definitely, right? But native element occurrences are also they are associated with magmatism as well as hydrothermal fluids. Okay, so hydrothermal fluids are acting, beneath the ocean floor, and they can have some association with magmatism. So they will dump some of these mineral deposits, and that will be available for the people to use in the future. And silver is also hydrothermal occurrence is there because they are rich in sulfides, arsenides like compounds as well, right? Sulfides, arsenides, and even bismuth containing bismuthides, right? Bismuthides we call bismuthides. And native copper, when at places where copper is found, you can still find silver also, right? Most of the cases, because their genesis is almost similar. And copper, again, hydrothermal ore deposits or secondary oxidation of copper sulfide minerals. So in rocks, we have copper sulfide minerals like pyrite, right? Pyrite, then arsenopyrite, like pyrites are there. So they are associated with sulfide. So therefore, they can be oxidated. So their sulfide becomes sulfate. Then the metal get released. So such accumulations are also found in the world. So therefore, the copper can be found in such places mainly. Okay, so native copper is produced in such kind of situations. And then platinum, it's a Pg metal, inert metal. Sometimes we call it inert metal or non-reacting metal as well, right? Like inert gas, right? Argon, krypton, xenon, they are inert gases, right? Because they are non-reactive. So similarly, there are metals which are not reacting, unlike iron, magnesium like things, right? So anyway, you can find copper in such places in hydrothermal deposits or secondary oxidation of sulfide minerals. And also platinum can be found associated with mafic intrusions. Mafic intrusions, right? Mafic intrusions means iron and magnesium rich magmatic bodies. And we have diamond. So, you know, diamond can be found in different places like mantle derived diamond as kimberlite pipes. So these are magma carrying pipes, right? So along with that, you had diamonds from very deep, right? Very deep part of the Earth's mantle, right? In such places and associated with such places, there can be some residual type of diamond as well. Residual. That means the eroded and deposited in low-lying basins. Alluvial, residual and alluvial, both types. Residual is just deposited close by to the origin, and alluvial is transported and deposited in low-lying basins. And sulfur, which is found as precipitates near volcanic vents. What is volcanic vent? That is the opening of the volcano to the outside environment. Okay. So sulfur can be found like that. Also, when sulfide minerals get oxidated, there is possibility for sulfur to be changed, and sulfate can be formed, or elemental sulfur can be formed. So if sulfate is produced, then there should be another method to be applied for purification of the sulfur. Right, so sulfide, we will consider some little more details on sulfides. So most common ore source of metals. So associated with sulfides, what you have is these metal sulfides. These metal sulfides prefer much these elements. So you can see here copper, zinc, lead, nickel, cobalt, mercury, molybdenum, arsenic, antimony, and bismuth. All can substitute for sulfur, right? So they can substitute for sulfur, and it will give rise to some other arsenic when it is arsenic. When it substitutes for sulfur, it will give rise to sulfur arsenides, right? Basically, sulfur arsenides means sulfur bearing arsenides. So that is rarely happening, not very much, but you know, these sulfides, they prefer anoxic conditions. Anoxic conditions means reducing conditions. As long as they are in reducing conditions, sulfide is very stable. So it's not easy to separate, decompose. For that, you need to have oxidizing conditions, right? When it comes to have some oxidizing conditions, then it can convert into elemental sulfur or sulfates. Elemental sulfur or sulfates. Then magmatic and hydrothermal origin is already there, as we discussed. That means related with hydrothermal deposits and magmatic flows, magma flows. Right, so in composition wise, again, the copper iron sulfide minerals are very, very complicated because they are also acting as solid solutions. They are also acting as solid solutions. So native copper, if you have here native copper, native iron, and native sulfur, right? If you consider this triangle with these three compositions at the corners, there will be variable products. There will be variable products. Okay. Right. So you can see they can form different types of products depending on their composition, copper, iron, and sulfur. Okay. Copper, iron, sulfide minerals means it's a mixture of these non-metals. That means sulfur bearing as sulfides, but in the anoxic form, right? Anoxic form. Right. So you have to oxidize them, then you can separate out the native element, sulfur. In the paper that I gave you also related with copper iron sulfide deposit, right? Copper iron sulfide deposit in Seruvilla, right? We have both copper and iron associated there in that different deposits in the world. So this copper and iron sulfides form together. That's why they form together in some regions. So you don't need to memorize all these compositions, but just keep in mind that they can also contribute to solid solution by mixing at various proportions of these cations. Right. So other common sulfide minerals, other common types of sulfide minerals, you know, galena, it's lead sulfide, galena lead sulfide, and sphalerite. Sphalerite is what? Zinc iron sulfide, right? Sphalerite, it's zinc iron sulfide. It's kind of yellowish substance, and have a resinous texture. What is resinous texture? It's a very dull texture. Then we have pentalite, that is iron and nickel bearing sulfide, right? And it gives a bronze color. It gives a bronze color in that particular mineral. Okay, right. So then mercury sulfide. So what is this mercury sulfide? Mercury sulfide is we call cinnabar, right? Cinnabar, HGS, mercury sulfide, mercuric sulfide. It's very reddish in color. It's more reddish in color, which also you can find in some hydrothermal deposits. Right? And then comes molybdenite. It's molybdenum sulfide. Right? It has a metallic luster with silver and ash color substance. Right? So it's a molybdenite. Some people get lost with the molybdenite for graphite, right? So they think sometimes molybdenite also similar to graphite, because in appearance, in some cases, you can see both look like similar, right? But it's a different thing. Molybdenite is molybdenum sulfide. So several more rare compounds are there, which we can consider as industrial minerals: arsenosulfides, arsenides, and sulfur salts. Arsenosulfides, arsenide, and sulfur salt. Right. Cobaltite. Cobaltite is cobalt and iron bearing arsenic sulfide, arsenosulfide, right? Then arsenopyrite. Arsenopyrite is there. Then real Ga. Real Ga is arsenic sulfide again, right? Real Ga. And opiment. Maybe you have, you know about opiment. Opiment, it's arsenic sulfide. Some very, very rare compounds are also there. Silver gray cubes, which you can term scuterudite. It's copper and nickel, cobalt and nickel bearing arsenic compound, arsenic sulfide compound. One is should come here. Okay. Then stibnite, antimony sulfide. Stibnite, it's acicular-like, right? It's mainly with some kind of pointed endings, right? That is what you call acicular type, stibnite. And then sometimes you might see as silver or gray prisms, silver or gray prisms. And one another rare sulfide is where you can use them as for extraction of some of these metals as well, right? Because they are associated with them. Enagite, copper, that is copper arsenic sulfide. It's striated metallic columns are there. And the other one is, which is copper arsenic sulfide, right? Copper arsenic sulfide, which we call a sulfur salt, right? Sulfur bearing mineral, but people used to call it sulfur salt, right? I'm not very sure as to why such a term is there, but anyway, it has striated metallic columns, Yeah. So these are the types of other types of industrial minerals which we can find, but they are not very common in the world. So that's why I mentioned about that aspect at the very beginning, right? So do you have any question regarding the content? If you have any question, please ask. And also remember, I haven't gone through any very specific detail because it's far beyond the scope of this course. But if you want, you can learn by yourself separately regarding other aspects, crystallinity, crystalline features, crystallographic features in mineralogical terms, right? But at this level, we are just introducing the occurrences of these types of industrial minerals. Otherwise, you will just, I mean, many of us will just think that, okay, this is calcite and marble only, right? No, it's not like that. Or even quartz or feldspar only, if you want to construct, or if you want to do some sort of development in some regions. Okay, do you have any question? So today, basically, we considered about the other types of mineral groups, right? Like oxide, sulfide, halite, likewise hydroxides. And then finally, we talked about the native elements as well, right? Native elements and sulfides, because those are the remaining types of other industrial group. And we haven't talked about anything on silicates, because somebody else might have talked about such some of those silicates like quartz, feldspar, basically, right? And in addition, maybe you have considered some other industrial minerals like graphite, diamond, and calcite, dolomite, right? Very specifically. But what I did was just we had some consideration about the rarely occurring other types of industrial minerals that we should be aware of. Okay, do you have any question? You don't need to memorize all those some very rare types of names, but just keep in mind at least how their composition I mean, at least in qualitatively, like for example, if you have a spinel, then you should know, okay, this can be either be considered as sodium oxide, magnesium iron oxide, right? In addition to that, sometimes you might have chromium and titanium also, right? So likewise, such some qualitative level of learning is sufficient for this course. Any question? So today I can finish my part of this industrial minerals section with this lesson. So you should remember what we have been talking about from the very beginning. That is about the industrial mineral and especially mining related aspects we discussed in much more details. So if you have any questions, so you can ask me. No questions? Okay, so then maybe you can, within the next week, can you please send your review of the paper? That means a sort of a briefing. After going through the paper, you can send me the brief description of what you learned about that. Okay. It talks about the copper apatite deposit in Servilla region, right? And also there is some comparison of ore grade gold and whether we have sufficient amount of gold in that deposit or not, right? So these type of aspects you can focus on and write down the briefing.